Hello, everyone. My name is Kristen Milbury, and on behalf of the Foundation for Conservation of Atlantic Salmon, I would like to welcome you to today's webinar. Today's webinar will be presented in English. However, we have AI translation available. If you wish to use the translation, please navigate to the chat where you will find instructions on how to connect. For today's webinar, we are very pleased to be hosting Dr. Christine Startini. Dr. Christine Tartini completed her Bachelor's of Science and Master's of Environmental Studies at Dalhousie University and her PhD in Theoretical Marine Ecology at Queen's University. She has worked for Fisheries and Oceans Canada since 2012 through her academic endeavors and since in many capacities. She has worked in the fields of geospatial climate change vulnerability assessment to support conservation planning and fisheries managers, species distribution models to predict climate change related shifts in commercial species distributions, conservation planning for climate change resilience, data management, science program coordination, and strategic science planning. Today, Christine will be speaking on Freshwater Climate Risk Index, a case study for Atlantic salmon in Eastern Canada. After this afternoon's presentation is over, we will be opening the floor for questions and answers. I will now turn the webinar over to Christine.
Thanks. Thank you so much. Hello, everyone. Thank you for having me. Today, I'm going to be presenting on a project that has been built upon since 2021. It was started in my previous role as an aquatic biologist in Maritimes region for Fisheries and Oceans Canada, and started by myself in collaboration with Daniel Boyce, Sarah Tuziak, and Amy Gromack. And then Megan Shin was our master's student who took on the process of expanding this framework that we had created to New Brunswick and Prince Edward Island, because it had originally started in Nova Scotia. So I'll be presenting about the framework that we created, and then showing some results specifically for Atlantic salmon. So first, I just want to acknowledge that this project wouldn't have been as successful as it has been without the input from many experts in the field of freshwater science. Myself, being a marine biologist, when I first started this project, it was a whole new world. So I really appreciate the advice and input that was provided by everyone that you see here on this slide. Okay, so a bit of an introduction into what a climate change vulnerability assessment is. They typically have three components: exposure, sensitivity, and adaptive capacity. Exposure typically characterizes the magnitude of impact that climate change will have on the environment in which a species exists. And sensitivity typically characterizes the sensitivity level of the species to continued change in the environment. And this is dependent on things like, is the species already imperiled? Has it been overly depleted? And I'll show you some of the indices of sensitivity in a second. Adaptive capacity is the third component. And this characterizes whether the species will be able to adapt or shift in distribution as a response to climatic changes. We took a climate change vulnerability assessment called the Climate Risk Index for Biodiversity, which was originally developed for marine species. This Climate Risk Index for Biodiversity was the first quantitative climate change vulnerability assessment that looked at all three of these components, which is sort of an internationally recognized format. Considered the effects of other stressors other than climate change on the species of interest, used big data sources, so data that are available across a global range so that this framework could be used anywhere in the world. And it was made to be generalized and flexible so that it could be used across multiple ecosystem types. So the concepts behind each of the indices that are included in this assessment were meant to be concepts that could apply across different ecosystem types. So we took this marine-based framework and adapted it for freshwater. As a result, some indices were removed that were deemed not appropriate in the freshwater environment, like global distribution range. And this was because we had an assumption that most of the species that we were looking at had homing mechanisms that led them to choose only specific areas to exist in. Proportion of global temperature ranges within their tolerance range and depth range, mostly because there weren't a lot of data to characterize the depth range of species in river systems. So we dropped those indices. And again, a lot of this was because of the assumption of watershed fidelity. And we focused our assessments on specific watersheds as opposed to the entire range of a species. Some indices were added that were not appropriate in the marine environment, but were appropriate in the freshwater environment, such as precipitation extremes. So acknowledging the fact that changes in precipitation amounts are going to happen as a result of climate change and will impact the species in freshwater environments. And then the human impacts that were included in this assessment were different than the human impacts that are relevant in the marine environment. Okay, so these are the indices within each of the three components of the vulnerability assessment, or the freshwater adapted crib. So under exposure, we had projected habitat loss of the species within the region of interest, the time of emergence from the thermal niche, so the time in which we expect the temperature will become too warm for the species in that area, the velocity of warming, so the rate at which the area is warming, and the magnitude of change in extreme precipitation events. In sensitivity, in the component of sensitivity, we had exploitation status, so that's Cusiwick status. Has the species already been depleted and therefore would make the population more sensitive to additional stressors? Thermal pressure or safety margin, so that is the temperature already very close to the upper thermal limit of the species, and therefore is it already getting close to its stress limit? The other anthropogenic stressors that the species is experiencing in the area that would make it more sensitive to further stress, and projected ecosystem disruption. So this is to try to incorporate sort of the more secondary influences of climate change on the system. Are there other species that this species might rely upon or interact with that are going to be negatively impacted within that area? And then in the adaptive capacity component, we had historical thermal variability. So is the species already adapt to extreme temperature changes, or extreme temperature fluctuations in the environment? What is the amount and connectivity of the habitat within the area of interest? So does it have a lot of places to run to if the environment becomes intolerable in a particular part of the region? And body size was used as a proxy for life history. So if a species is smaller bodied, it typically reproduces much more quickly and therefore could evolve or adapt at a population scale more quickly to changing environmental conditions. Each of these indices are quantitative, so they're based on real quantitative data, and then they were scaled from a scale of 0 to 1. And we tried to ensure that all the data that are used to characterize each of these indices were broadly accessible as possible, so that this framework could be adapted to other regions within Canada or abroad. Here's a schematic of what this framework looks like. So the input data are on the top, and those data were put into each of the indices, which were then averaged. And then the inverse of the standard deviation was used to weight the scores based on the component level scores based on the variability of the index level scores. So if within the sensitivity component, the 4 indices had very different scores from 0 to 1, then the sensitivity score would be downweighted in the overall average to get you a final vulnerability score. And then the next step was to translate this vulnerability score into a risk category. And this was based on, for each of the indices, there's a relationship between the quantitative value of the index with an extinction risk or a risk that the ecosystem will not be able to recover from that negative influence. And so we used that relationship to determine, and it was also based on global best case scenarios and worst case scenarios to cap the values. So we used the relationship and those caps to determine the sort of bins for low risk, medium risk, high risk, and critical risk. So for each of the indices, we had those values, and then we were able to run those values through to the vulnerability score at the end. So we have vulnerability scores that are binned according to risk. So when a species falls within that bin, we were able to characterize it as low risk, medium risk, high risk, or critical risk. And if you have any questions about that process, I do have an additional slide to maybe explain it a bit better. So we ran the freshwater crib for Nova Scotia first, and then expanded the analyses to New Brunswick and Prince Edward Island. So that was Megan Shin who did those analyses. And these are just some of the species that were assessed. So Atlantic salmon, American eel, Atlantic whitefish, striped bass, brook trout, alewife. But for this presentation, I will be focusing on Atlantic salmon. So I just wanted to run through the data sources that were used for each of these indices. So for the indices that are based on climate change projections, we got the data from climatedata.ca. There were 24 statistically downscaled climate scenario datasets for under three emission scenarios. So SSP 1 2.6. So that is sort of our best case scenario if we continue to reduce emissions. A middle ground scenario, which is SSP 2 4.5, and then a high risk scenario. So if we continue to emit at the rate that we are and actually slightly increase our emissions globally, that's our SSP 8.5. So for three emission scenarios, we got 24 statistically downscaled climate models. And from those models, we had outputs of monthly mean and maximum near surface air temperature at a 10 kilometer squared resolution up to the year 2100, as well as monthly precipitation totals, again, up to the year 2100. Unfortunately, there were no projections of water temperature. And so we had to use air temperature as sort of a proxy and look through the literature to find instances where researchers have compared river temperatures to air temperature and found that on average, depending on groundwater influence, there can be a difference of 3 degrees, where the water is 3 degrees cooler than the air near surface air temperature. So we took the air temperature data, reduced it by 3, and that was sort of the best that we could do at the time. Hoping, again, that in the future this could be rerun with actual projections for water temperature that account for groundwater influence. So these are some of the indices that that used those climate data. So we produced time series of maximum monthly mean temperatures. And then we looked at the thermal tolerance of the species and then found the year from the time series of temperatures from the projections, the year at which the temperature would become too warm for the species. And then that's the time of thermal emergence. The thermal safety margin, similar concept, a time series of the maximum monthly mean temperatures from those projections was developed. And then we compared the historical time series up to the year 2021 with the species upper thermal tolerance. And so I'm just using 20 degrees as an example here, and then looked at the difference between that upper thermal limit and the maximum of those maximum monthly mean temperatures that the species has experienced in the area up to this point. So how close is it currently to its upper thermal limit? And then for climate velocity, we looked at the projections, but looked at the direction of change. And this was using an R package called VOCC, so the velocity of climate change in R. So it accounts for the rate of change, but also the directional change. And the reason for that is because this will influence a species distribution. So it's pushing it in a certain direction. And so we wanted to account for that. Okay, and for precipitation change, we looked at the average proportion of extreme, and we considered extreme to be precipitation levels greater than 1 standard deviation from the long-term average up to 2021 in days per year over the 2075 to 2100 projected time frame. So within the 2075 to 2100 time frame, how many of those days are projected to be extreme in precipitation? And this was to account for extreme days in the positive direction, so potentially flooding, resulting in flooding, but also in the negative direction, so could indicate drought. So for exploitation status, as I mentioned before, we used the statuses from the Committee on the Status of Endangered Wildlife in Canada to look at whether they were not endangered, if they're endangered, threatened, or special concern. And then for our body size as a proxy for life history, we got body size either from local literature on a species. So an example was for Atlantic whitefish. We couldn't find the data on FishBase, but so we looked through the literature. But otherwise, we got maximum body size from FishBase, where there's a record for most species and literature are cited. For other anthropogenic stressors and amount of habitat and connectivity of habitat, we got these data from the Nature Conservancy of Canada. So they've got some great spatial data sets of cumulative human impacts and climate resilience, which included habitat connectivity and diversity. And so that's where we got those data. This is what it looked like. The data are pretty fine spatial scale. So our analyses, given the spatial scale of the other indices, or the data for the other indices that we wanted to characterize, were at the primary watershed level. We took an average of these sort of tertiary watershed scale data up to the primary watershed level. Okay, so I'm going to run through some results of running the freshwater crib assessment for Atlantic salmon across those 3 provinces. We had a maximum temperature tolerance of 20 degrees Celsius for this species. And this was based on a lot of literature describing when the species seems to seek out thermal refugia, so cool water pools, also laboratory experiments that determine stress levels. And we took an average also across a couple life history characteristics, life history stages, and determined that 20 degrees would be a conservative estimate. Some papers were indicating that it could be higher than this, but to be more of an indicator of how stressed the species might become, and before the species has only a few cool water refugia to seek out and nowhere else to go, that's why we chose 20 degrees as a conservative estimate. Okay, so using the climate change projections within these 3 provinces, we looked at Atlantic salmon's predicted habitat loss by the year 2100. So this means the primary watersheds where the species Atlantic salmon is predicted to breach its upper thermal tolerance limit by the year 2100. So under the low emission and sort of mid-range emission scenarios, so 2.6 and 4.5, we find that Atlantic salmon does not emerge from its thermal niche in these 3 provinces by the year 2100, except under a high emission scenario, it emerges almost everywhere except for 3 primary watersheds in southwestern Nova Scotia and Grand Manan Island in the south of New Brunswick. The time of thermal emergence, again, for the 3 future climate scenarios or emission scenarios. So this is the year in which we predict the Atlantic salmon will reach its upper thermal limit within the primary watershed. Again, within the low emissions and mid-ground emission scenarios, we find it does not reach its thermal emergence by the year 2100, but under the high emission scenario, you find it's most vulnerable in Prince Edward Island and around the southern Gulf of St. Lawrence. And here's just showing what that looks like when you translate those vulnerability scores. So the value of the year in which it's projected to emerge, translate that value into the score from 0 to 1, and then into a risk characterization. We find high risk in Prince Edward Island and southern Gulf of St. Lawrence area. Velocity of warming had low vulnerability across the majority of the primary watersheds in these 3 provinces, except about some medium risk areas in southwestern Nova Scotia, Prince Edward Island, and again around the southern Gulf of St. Lawrence, but this time in New Brunswick. And then for the magnitude of change in extreme precipitation, we found that there was a low risk, and I'm just going to explain that the vulnerability scores here, you'll notice that the scale is not from 0 to 1, and that's just to allow you to see some of the spatial variability, because if we had a scale from 0 to 1, it would all be light yellow. So when you look at the translation to risk, it's low risk for all primary watersheds under all 3 future climate scenarios. So that means a low risk of extreme precipitation days based on greater than 1 standard deviation in the 2075 to 2100 time range. Exploitation status. So this is just a visual depiction of the COSEWIC statuses of Atlantic salmon. Thermal pressure safety margin. So again, this is how close the species is to its upper thermal limit currently. So currently we have critical risk across the majority of the primary watersheds, although I guess it's going to take some time still to actually reach the limit based on the climate change projections we have. So it's high risk or critical risk even under the low emission scenario. So that gives you a sense that it's pretty close already present day. Other anthropogenic stressors. So here's the vulnerability index values in the top figure, and then translated into risk categories in the bottom. So we had low risk from other anthropogenic stressors in quite a lot of watersheds, although it was medium risk for the majority in the central areas and for Prince Edward Island. One watershed in particular had critical risk. I believe that's Lahave in Nova Scotia. And this is based on data that provide characterizations or quantification of the number of unpaved roads, impervious surfaces, the instances of non-native fish, percentage of aerial coverage of clear-cut forests, so the intactness of the watershed, cropland, pasture land, point source pollution, acid deposition, and leaching. So it's an average of all of those negative influences from other human activities. Projected ecosystem disruption. So again, this is the proportion of species that all the other species that were assessed, the percentage of those species that are predicted to reach their upper thermal limit within the primary watershed by the year 2100. So how many other species are predicted to disappear from the area by that year? We find under the best case scenario and middle ground scenarios, there's low risk of ecosystem disruption, but under the high emission scenario, there's critical risk across all primary watersheds in the 3 provinces, except for, again, a few watersheds in southwestern Nova Scotia and Grand Manan Island in New Brunswick. Okay. Right. I wanted to show you that if you were to use a different characterization of a species upper thermal tolerance limit, it changes the risk quite a bit. So for the majority, for the assessment, we used an average of the critical limit, so the physiological limit of a species after which the species dies, or the sort of stress limit where the species becomes quite stressed. We took the average of the two. But if we were to take just that lower limit, the non-critical limit, we get critical risk across all three climate change scenarios. Okay, historical thermal variability. So this was what is the variation in the temperature of the primary watershed, or what has that variation been since the year 2015? And so could we infer then that the species is tolerant to variable temperatures already? We found that there was medium risk to the species. So that means that it's not completely adapt to variable environment currently, which would mean that it had a low risk here, but it's not critical. So the amount of habitat, the kilometer squared of aquatic habitat available within each of these primary watersheds. We find that there is not a lot of aquatic habitat available within Nova Scotia and Prince Edward Island, so high, medium and high risk in those areas. But in New Brunswick, particularly in St. John's watershed, there is a lot of aquatic habitat available. But then when we look at connectivity, so this is the density of roads, dams, culverts, and they're weighted by passability. So when we're looking at dams, that means if they're the presence of a fish passage. And these data were taken from the aquaticbarriers.ca website. And I think since we ran this analysis that those data have been updated, so this will need to be reassessed. We found that there was critical risk across the majority of primary watersheds because there are quite a lot of dams, culverts, and roads, except for a few watersheds in southwestern Nova Scotia. Body size is a proxy for life history. So Atlantic salmon had a maximum length of 150 centimeters, so it was placed in the low risk category for this index. Overall vulnerability for Atlantic salmon in these three provinces led to a low risk characterization under the low emission scenario and mid-range emission scenario. But under a high emission scenario, there was medium risk across the majority of watersheds, except a high risk in Prince Edward Island and southwest and the southern Gulf of St. Lawrence primary watersheds in Nova Scotia, and a low risk in the southwestern Nova Scotia. And so this just shows that you can get a spatial characterization of overall vulnerability that accounts for all of those indices that I just presented on, which gives you a general idea of the risk of the species, but then you can dig a little bit deeper and go back into the indices themselves. And so that's sort of the value of an assessment like this, where you can spatially characterize each of the indices alone, but then sort of have that high level overview of the overall vulnerability as well. Okay, so how can these data potentially help freshwater management? And again, it's very important to consider the overall vulnerability within the context of the individual's index scores. So we can use the vulnerability as a base level to assess areas that might be high risk, but then you use the indices to understand why that particular area might be a high risk for the species of interest. Low climate vulnerability areas could be protected as refugia for a species. So if the area is generally pristine habitat and not predicted to change very much, that might be an ideal habitat. Low vulnerability areas where the species is currently not observed could present opportunities for reintroduction, and so those could be ideal target. Low vulnerability areas with high impact from other stressors might require remediation if they want to, if a manager might want to target those areas for classification as a refuge. High climate vulnerability areas with low impact from other stressors could be monitored for change. So these might be, really good test areas to see how the ecosystem might change over time, and monitor as the species reaches its upper thermal tolerance limit. Okay, and one thing that I wanted to note is that this assessment was a really good first step, and I think provides some really great high-level information characterizing risk based on atmospheric warming within these 3 provinces. And the same approach could be used elsewhere to characterize risk. But one major caveat that we are hoping to address in the future is that it doesn't account for the influence of groundwater, and that's because the data just simply weren't available at the time. So this idea that groundwater can influence the temperature of a river or stream and therefore buffer it against warming of the atmosphere. And this is just a figure that was provided to me by Antoine O'Sullivan, who was previously with the University of New Brunswick, that shows the range of temperatures in the air versus the temperature in a groundwater fed stream. And you can see that there's quite a lot of difference. So in the case that a river has a lot of groundwater influence, then we would need to sort of downplay the impacts of warming air temperatures that were predicted based on the data from climatedata.ca. Okay, so the next steps for this project, we are still working on a primary publication case for the case study on Atlantic salmon in those 3 provinces using the results that I just showed you today. But we'd also like to evaluate Atlantic salmon vulnerability in the marine environment using the original marine-based climate risk index for biodiversity, the CRIB. And up there in the top right-hand corner, you'll see what hypothetical results from that assessment could be. And then the combination of vulnerability in the marine environment and the freshwater environment could be used to assess the overall vulnerability of populations that have different life stages in different environments, so in the freshwater and in the marine environment. We're also working on proposals for future work. Again, as I previously mentioned, we'd like to incorporate models of groundwater influence to either improve or weight or adjust the indices of warming. We'd like to incorporate genetic adaptivity indices that are being developed under the GenArc project in collaboration with the researchers that are working on that project in Newfoundland. And we'd really like to start workshopping these results with decision makers in recreational fisheries management, conservation, recovery planning, and restoration with program sector or stakeholders, employing risk-based decision-making frameworks. So these data provide you with your level of risk, but then there's a whole other step that needs to be taken to understand what that risk means to you, what level of risk you're willing to accept, and which direction you would want to go in based on the knowledge of that risk. And so what does that mean for these various stakeholders and program sector representatives? Okay, so that's it for me. And if you would like to contact me, I've left my email here. I also have the link to our master student, Megan Shin's thesis, where the sort of expanded results from this project for many other species are included. And again, huge shout out to Megan for pulling all of this together and for getting us on the right direction. Thank you very much.
All right, awesome. Thank you so much, Christine. Excellent presentation. So we will now open the floor to questions. If you have a question, please click the little hand icon on your screen to raise it. and then I'll be able to unmute you and you can ask your question. Also make sure that you are unmuted yourself. This would be the preference, but if this function does not work, you can type your question into the chat and I'll read it out loud for Christine to answer. Okay, it looks like we have the first question from Kate Vay. You can unmute Kate, you can ask your question. Go ahead and unmute Kate. Oh, she might be having difficulty here. I'll try again. If there's any other questions that I can call to, just raise your hand. Okay, let's go to Bill Haley. You can unmute Bill and ask your question.
Hi, Christine. Very interesting. Bill Haley from Marguerite Salmon Association. I was just wondering, when you were talking about the difference between the water temperature and the air temperature, did you say that typically that you were using a 3-degree difference?
Yeah, and this was based on data collected by fisheries and oceans researchers in some of the rivers across Nova Scotia and New Brunswick, where they collected air temperature and water temperature at the same time.
I'd suggest here would be quite different.
Okay.
We have a warm water protocol and we track both the air temperature and water temperature. And typically, you'll see days that will be 30 degrees with water temperature maybe 22, and that would be typical, you know. So I guess this part of the woods it might be a little different, but we do have a lot of groundwater in our river.
Okay. Yeah. Yeah. So it's tricky.
Can I ask another question? Is while I have you here?
Yeah, of course.
The proxy where you were using small fish to evolve or to change faster than large fish. I don't know if I understood that very well. Like typically when I think of fish by mass, the larger fish would have more eggs and there'd be more um, small fish introduced to the watershed, and that probably I would think that would have an impact on more evolution if you have more fish. But maybe you could say a few words about that.
Yeah, it's more about generation time, like how quick to reproduce and then die, and then the next generation takes over. But I have heard that while that concept might apply very well to marine fish, that there might be several exceptions to the rule in the freshwater world. And so that might be an index that we could consider further adapting, that maybe it doesn't work in the freshwater environment as well as it does in the marine environment.
It's quite possible. Anyway, thank you very much. I found your presentation very interesting.
Thank you very much.
Thanks, Bill. Okay, it looks like Kate's working again, so you can go ahead and unmute Kate and ask your question.
Hi there, is this working now?
Yep.
Yes.
Awesome. This actually isn't Kate. This is Annie McMullen. I'm here with Kate. We're with the Kennebecasis Watershed Restoration Committee in New Brunswick. So we work on the Kennebecasis River. And on your map, I know that you said that New Brunswick has good salmon habitat, but because of the fish barriers, they're a bit more vulnerable. Do you think it would be like a better option to focus on removing the barriers or providing additional habitat maybe further north?
Yeah, that's a great example for kind of looking at the balance between the different indices. Maybe focusing on removing barriers from a watershed that has a lower climate vulnerability would be the way to like prioritize actions like barrier removal.
Okay. Okay, awesome. Thank you, Christine. We were just kind of curious because we do a lot of habitat restoration and we do work a lot with agricultural landowners. So we focus a lot on implementing more BMPs and making more of that shelter belt buffer to make the waters a bit more cool. And yeah, we were just kind of curious of your thoughts for the Kennebecases specifically, if you had any insight there.
I'm not sure about any specific areas. Unfortunately, I'm more of looking at this from a really broad scale, but I hadn't really thought about the fact that removing barriers would further reduce temperature. That's really interesting. So thank you for bringing that up. Something that I didn't know. But yeah, in my opinion, based on the data and sort of the idea that it would be potentially more forward thinking to focus your efforts and your time and your money on areas that are going to, like, if you put in effort to restore an area, that the temperature is going to be within the tolerance range of your species and well into the future, that might be a consideration. So that would be, looking at the time of emergence index, for instance. But another hope of ours is to downscale this assessment. So right now it's at the primary watershed level, but we could go a bit finer scale and look at specific rivers, which might be even more useful for things like restoration efforts. So if you're interested in sort of keeping abreast to the developments of this project, I'd love to for you to send me an email and I can try to keep you in the loop.
Thank you. No, that would be awesome. We will definitely be emailing you. And thanks again for the presentation. That was very well done.
Thank you.
Okay, great. Thanks, Kate. So the next question is from Ilias Hanny. Go ahead and unmute Ilias and you can ask your question.
Hi, Christine. I am a PhD student at INRS working with André Saint-Hilaire. We're modeling rivers. We considered like 40 rivers around Eastern Canada. A lot of them are stated in your within your study region. And we did some climate change projection for water temperature and discharge at a daily time step so we have data basically from 1979 to the end of the century, distributed across several watersheds. That's the one you presented. So if you guys are interested in this kind of variables, it would maybe help develop the model considering the water temperature projection data.
That would be fantastic. That's very exciting. Yes, I would. Would you mind maybe sending me an email? I would love to be in touch about this.
Yeah, sure. Okay, I will talk with my supervisor and I'll be glad to connect with you.
Okay. Thanks so much.
Thank you very much.
Great. Next question is from Jeff Giffen. Go ahead, Jeff. You just got to unmute there and ask your question, Jeff. Okay. While we wait for Jeff to unmute, we'll go to, there is one question in the chat from Gerald Chaput. He asks, a lot of work, thank you for your presentation. Follow-up question on temperature scaling. -3 to go from monthly mean air to water may apply in summer but not in the winter. Was the thermal index calculated only during the summer period or on the summer period?
Yep, that's a good point. But we did only consider summer temperatures because we were looking at the maximum values usually per year to evaluate when it would become too warm. So we didn't really consider any winter specific adjustments. But if we were looking at lower values, and another idea of ours actually was to look at when the lower limit of values over the year might become tolerable for incoming species. And so that's where that might come into play, and we'd have to reconsider the adjustment. But also, really ideally, we would like to have water temperature values as opposed to atmospheric, and we're working on it.
Okay, great. If there's no other questions, which it doesn't look like there are any right now, let me just double check. Okay, no, there is one that just came in. The question is riparian integrity considered to be a variable?
Oh, I'm not sure if I quite understand that question. Pairing integrity?
Riparian.
Oh, riparian integrity. Well, it's indirectly accounted for through the cumulative impacts index, where we looked at things like forestry and paved areas, and sort of these activities that do negatively influence the habitat, riparian habitat. But we didn't have one index that was directly about the sort of intactness of riparian habitat.
Okay. I'll give it one more second, but it looks like that might be it for the questions. It's great. We had a lot of questions. Thanks so much, Christine. If someone does come up with a question later, please feel free to reach out to Christine using the email she's provided. You can also contact the foundation and we'll pass her information along or connect you both. We have recorded the session and it will be available on our YouTube page later today. And I would also like to remind everyone that our next webinar will be held on March 26th with Dr. Kurt Samways, Freshwater Ecologist and Parks Canada Research Chair at UNB and Canadian Rivers Institute. The title of the webinar will be Reconsidering the Role of Salmon and Other Anadromous Fishes in Freshwater Food Webs. Okay, great. So a big thank you again to Christine and to everyone who participated today. We'll hopefully see you at the next webinar. Thanks, Christine.
Thanks so much.